Hello, this is Mrs. Ward, and I'm going to go over the notes for section 5.6, the summary curve section. So what we're going to do in this is we're going to analyze the sketch graph of a function, hopefully without using a calculator. So just to remind you, some of the part of this page here is everything that we've already done throughout the course of the year, and in Algebra 2, we refreshed it this year. So my x-intercepts are when y is equal to 0. My y-intercepts are when x is equal to 0. So if I have any equation, I want to find my x-intercepts, I substitute 0 for y, solve. If I want to find my y-intercepts, I substitute 0 in for x, and solve. These are also called the zeros of a function. And if I have a rational function, in other words, I have a numerator and a denominator, to find the x-intercepts are the zeros, I'm going to set the numerator equal to 0. That is going to give me my x-intercepts. To find my y-intercepts, I'm going to put 0 in for x and solve. Just up there. The domain is all the possible values of x. So that's what x is allowed to equal. The range is the value of the y values. In other words, if I graph it, what y values do I reach? So it's so if I had f of x is equal to x squared plus 3 plus 4. If I do that, because I know the factor is x plus 2 squared. If I had something like that, my domain is going to be all real numbers. I'm going to write that with or I can write negative infinity to positive infinity because I can put in any y values that I want. If I graph it, it's going to be a parabola something like this. So my range is going to be my y values, which is going to be y is greater than or equal to 2. So that's going to be my range. If I have a rational function, remember the domain is the values of x. Like you have to list your restrictions if you have something that x cannot equal. Continuity remembers when the function is continuous. So to be continuous, I have no jumps. I have no vertical asymptotes. I have no restrictions on my domain. Vertical asymptote, again, is when I have if I have a rational function, I have a numerator and a denominator. The vertical asymptotes are going to happen when the denominator is equal to 0. And it doesn't simplify. And does not simplify. So just to remind you, if I had something like x plus 2, x minus 1 over x plus 2, x minus 3, here for my domain, going back to my domain, I'm going to say all real numbers, but x cannot equal negative 2, x cannot equal 3, because those are my restrictions on my domain, because that would make my denominator equal to 0. But since this factors out, remember that makes a whole, so not a vertical asymptote, since this one does not simplify out, the vertical asymptote would be x equal to 3. And then remember, we learned how to find the whole. We would substitute negative 2 back into what was left, and then we would find the place of the whole. Remember, differentiable, I can't even say it. No, so this is when you can find the derivative of the function. In other words, the function has a slope. So there's, if it's not a continuous function, you cannot find the derivative. But if it is a continuous function, there are some places where you cannot find the derivative. So you have no derivative when you have that, like the absolute value, or when you have that sharp curve, there's no derivative at that point. Also, there are some places, especially like if you have square root, when you start the function, it'll go something like this, and at this place here, you actually have a vertical tangent line. It's not differentiable there. Okay, relative extrema, that's when my first derivative is equal to 0. Those are my critical numbers, and then I can substitute those in. That means it's the highest point on the curve, so if I have a graph that goes something like this, this is my relative max, this is my relative min, but not necessarily the overall max or the overall min. concavity, remember that's when I find those by finding my hypercritical numbers, and I set that equal to 0 or when it's undefined. I guess I should put that up here too. And then concavity, if it's concaving up, your second derivative is positive. We just did this, and that means you're scooping up. And then if it's concaving down, that means your second derivative is negative, and it's sort of scooping down like that. Points of inflection are also going to be your height when your hypercritical number is equal to 0. And if I have a graph that goes like this, so at the point where I stop concaving down and start concaving up, like this point here, that would be my inflection point. To find it, I when the second derivative is equal to 0, and then whatever that number is that I get for x, I substitute all the way back into the original equation. Horizontal asymptotes, we just went through those on 5.5. You have whether you have to look at the degree of the numerator compared to the degree of the denominator, and then we follow those rules. So if I had like 3x squared with other stuff, 2x squared with other stuff, then my horizontal asymptote, since these degrees match, would be y is equal to 3 halves. Cross this out, you get 3 halves. If I have like 3x over 2x squared, where the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is going to be y is equal to 0. If I had 3x squared over 2x, and if I simplify that, I would end up with 3x over 2. So now I have a degree higher in the numerator than I do in the denominator. There is no horizontal asymptote. And then remember the slant asymptotes occur when you're 1 degree higher in the numerator. Then we did this is 5.5. We just did this. The limits of infinity at infinity, so that's my end behavior. And we did that yesterday or the day before, so we're great. All right, analyzing for graphs. So what I'm going to do is I'm going to determine the domain and the range of the function. I'm going to determine the intercepts in the asymptotes of the graph if I have any. And that includes all asymptotes, both the vertical and horizontal asymptotes. Then I'm going to find the values for which the function is the first derivative. So I'm going to find out when the function is increasing and decreasing. And then I'm going to find when the function is concaving up or concaving down. And then I'm going to sort of put that in my head. And then I'm going to find any relative extrema along the way. So the goal of this is for you to be able to do this with your calculator, and for me to block the graphing from the calculator so you still have access to the calculator, but not any of the graphing. So we did this, so go back to 5.4 and look at this, and I don't want that. Okay, so I have this, so we're going to, I have a nice chart. Let me go find that nice chart. Where is it? It's here in your notes. So when I look at your notes, I put this on your notes. So this sort of explains everything that we did in when we've done in chapter 5. So we talked about the first derivative, we talked about the second derivative, we talked about like when it's increasing, when it's decreasing, how I find the extrema. We talked about all that. So you have that, just look at, study. No, I will never do that to you in a test or quiz. All right, so here we go. I'm going to do this guy. So it's asking me for the type of function. Well, it's something raised to the third power, so I'm going to call it a cubic function. Not really important that you know the name, but it does tell me some things. I do realize that the degree of this is odd. The degree of this is 3, which is odd, which means I'm going to have different end behaviors as I look from the left to the right. Since my lead coefficient is that positive 2, that means I'm going to start low and end up. So that will look something like that. My intercept, so if I want to find my y-intercept, that means I'm going to set x equal to 0. And when I set x equal to 0, I'm going to get 2 times 0 cubed minus 3 times 0 squared, and that's just going to be 0. So I'm going to have a point 0, 0, and I'm going to go ahead and plot that. 0, 0. Then I'm going to have my x-intercept, which is when y is equal to 0. To make y is equal to 0, I'm going to set the whole thing equal to y. And then I'm probably going to factor out an x squared to make this 2x minus 3. So now x is equal to 0, and 2x minus 3 is equal to 0, so x is equal to 3 halves. So I have 0, 0, so this point gives me 0, 0, and it has a multiplicity of 2 because this is squared, which if we remember, it's going to bounce there. Remember that. And then x is equal to 3 halves, so my other order pair is 3 halves, 0. 3 halves is 1 1/2, 0. So 1 1/2, 0. So I'm going to plot those points. Then continuity, or it's a continuous function because I don't have a derivative. I don't have a denominator. I don't have a radical. I'm not a piecewise function. So it is continuous. And since it's continuous, my domain is going to be from negative infinity to positive infinity, are all real numbers. So I have no restriction on what my x is equal to. Then it wants me to find my limits at infinity. So my limit as x approaches positive infinity, it wants me to find, and it wants me to find my limit as x approaches negative infinity. So first of all, let's talk about the asymptotes. I don't have a rational function, so I'm not going to have a horizontal asymptote. So I don't have one of those. Since my domain is continuous and there's no restrictions on my x, I have no vertical asymptotes. So in this case, I have none. I have no horizontal asymptotes, no vertical asymptotes. So for asymptotes, I'm just going to say none. Limits at infinity. Remember, this is where I remember that it's an odd function, 3 of 3. Since it has lead coefficients of positive, it's going to end up, start low. End up is when x is approaching the right, so this is going to be positive infinity. As x approaches negative infinity, it's going to be negative infinity. So I could draw myself a note here saying that I'm going to end up, start low. Then it says increasing and decreasing. So to find increasing and decreasing, first I'm going to find the first derivative of that. So I'm going to copy down that function because x is minus 3x squared. I'm just copying that down for my benefit. Now I'm finding the first derivative. So when I find the first derivative, I get 6x squared minus 6x. So I'm going to set the first derivative equal to 0 to find my critical numbers. So now 0 is equal to, I'm going to factor out 6x, and that'll be x minus 1. So here x is equal to 0 and x is equal to 1. Then I'm going to ask myself, when is the first derivative undefined? And that doesn't happen. Then I go over here and I make the table because I'm trying to figure out when I'm concaving up or concaving down. So my two critical numbers are 0 and 1. I'm going to pick numbers to fill those out, and then this function factor is 6x and x minus 1, and then here's a place for my answer. So if I put in -1, I'm going to have a negative and negative. Negative times a negative is a positive. If I put in 1/2, I'm going to have a positive, negative, negative. When I put in 2, positive, positive, and positive. So my function is increasing from negative infinity to 0, and it's also increasing from 1 to positive infinity. It's decreasing from 0 to 1. So I'm going up here. I'm going up here. Up here, but I don't know how it's concaving yet, so I'm going up here. This little guy here, I'm going down, and then I'm going up. Now, just sketch that or just remember it. Pencils are great, you know that. Okay, concavity. So I'm going to. It asked me for my extrema. It did. So here I'm increasing, and then I start decreasing. So 0 is going to be a relative max. I'm going to have a relative max at x is equal to 0, so I put 0 back into the original equation. So I put 0 back into here, way up here, which I've already done, and I get 0. And then I'm going to, so decreasing, decreasing, decreasing. At 1, I start increasing, so I'm going to have a relative min at 1. And to find out what that is, I'm going to put 1 back into that original equation, which I have not done. So I'm going to find f of 1, and then you can do this in your calculator. 2 times 1 to the third minus 3 times 1 squared, and that ends up equaling negative 1. So I have an order here 1, negative 1, and I have this order here 0, 0, which I've grabbed 0, 0 a couple times, and now I have 1, negative 1. So let me go up there. 1, negative 1. 1, negative 1. So now I'm going to put this point here. Okay. And then I'm just going to talk about concavity. So I'm going to go up here to my first derivative, which was this 6x minus 6x squared. So my first derivative was 6x squared minus 6x. And now I'm going to find the derivative of that. And I'm going to get 12x minus 6. I'm going to set that equal to 0. So 0 is equal to factoring out 6 times 2x minus 1. So then when I set that equal to 0, divide by 6, 2x minus 1 is equal to 0, x is equal to 1 half. So I'm going to go over here, and I'm going to find 1 half, and then I'm going to take my second derivative, which is 6, and then 2x minus 1. Hit the numbers, so let's say I hit 0 and 1. Answer, oopsie, wrong place. So let's say 0 and 1, and so answer. So if I put in 0, this is going to be positive, put in 0, this is going to be negative, If I put in 1, this is positive, this is positive. So it's going to concave down from negative infinity to 1 half, and it's going to concave up from 1 half to positive infinity. Since I have a sign change here, that means I have an inflection point at x is equal to 1 half. So I'm going to find f of 1 half. So going all the way back to the very beginning, I'm going to take 2 times x to the 2 times 1 half to the third minus 3 times 1 half squared. So 1/4 maybe minus 3/4. So what, negative 1 half? And I don't know if I trust my math on that one. Let's do that. 2 times 5 by 2. Third power. Minus 3, let's see, it's not that, it's more, minus 3 times 5 by 2 squared. 1 half, why don't we do this? So I'm going to plot the point 1 half, so my inflection point is going to be 1 half negative 1 half, and I'm going to go ahead and sketch that. 1 half negative 1 half. So here's another. So if I remember, I'm increasing from here to here. I'm increasing from negative infinity to 0, and at that time I'm concaving down from 0 to 1 half. So I'm still increasing. So I have to get that. So I'm going to go like this. Increasing in here, start decreasing, still concaving down. At this point here, I start increasing up to this point here, which is a relative min, and then it goes up. And that is going to be my graph. I can check on my calculator if I let you choose. That's what I have to have. I have to get my zeros. I have to get this. I have to have this concaving down right here. It has to have sort of a bend in the graph, and then I have this. I'm still decreasing. Here I start increasing again, and then okay, moving on. Just checking. All right, here I have a rational function, and looking nice, I gave you the first derivative and the second derivative. What a sweetheart I am. All right, what type of function is this? This is a rational function. So with a rational function, I'm going to have more action. I'm going to have some places where I might have a vertical asymptote, definitely have restrictions on my domain. So my intercepts, again, my y-intercept is when x is equal to 0. So if I put 0 into this original equation, I'd have like 0 squared plus 1 over 0 squared minus 9. And when I do all that, I'm going to end up with negative 1, 9. So I'm going to have the order pair 0, negative 1, 9. So 0, negative 1, 9. Let's just put like a little dot there. Okay, good enough. Now I'm going to do an x-intercept. So now I'm going to set this whole thing equal to 0. Remember, when I set this whole thing equal to 0, I'm only setting the numerator equal to 0. I'm going to take x squared plus 1, set that equal to 0. X squared is equal to negative 1. Go take the square root. That is not possible, so there is no x-intercept. So I should not cross this x-axis at all. That's what I'm telling myself. All right. Continuity. So if I go back up here and I look, my denominator is x squared minus 9. X squared minus 9 is my denominator. That factors is x plus 3, x minus 3. So it's not continuous at x is equal to 3 and x is equal to negative 3. Those don't simplify. So my domain is going to be all real numbers. So that all real numbers, negative infinity to positive infinity, but x can't equal 3 and x can't equal negative 3. So since they don't simplify, they do not simplify, then I'm going to have a vertical asymptote at x is equal to 3 and x is equal to negative 3. Before I answer the other part of the question, I'm going to sketch those vertical asymptotes in. I like to use a highlighter for that. So 1, 2, 3, vertical asymptote. 1, 2, 3, vertical asymptote. Okay, so I have my vertical asymptotes. Remember, I cannot cross those vertical asymptotes at all. Then when I talk about my limits at infinity, that's why I talk about my end behavior, which means I have to look for any horizontal asymptotes. So here I see the degree of this is 2, the degree of this is 2. So those are the same degree. So it's like crossing this out, just looking at the x squared over x squared over x squared, which simplifies to 1, which means I have a horizontal asymptote at y is equal to 1. Now I'm going to sketch that in, but knowing that my horizontal asymptote, I may cross it, and that's okay. I may not, but I may. It's allowed. It's just that as I go this way, it's going to be 1, and as I go this way, it's going to be 1. But it may shift around there. Well, it has to, because I'm yeah. So okay, moving on. Increasing or decreasing. So that's where I look at my first derivative. So here's my first derivative, and I'm going to copy that down here. So my first derivative was told to me as negative 20x over x squared minus 9, and I believe that was squared. It was. So I am going to find my critical numbers. So I'm going to find when the numerator is equal to 0. So that's like 0. So that means I'm going to take my numerator and set it equal to 0. And that happens at when x is equal to 0. So that's going to be one of the places. And then I'm going to find when my derivative is undefined. And that's going to be when this x squared minus 9 squared is equal to 0. So remember, that's going to be when x is equal to 3 and when x is equal to negative 3. So when I go to make my table, I'm going to put negative 3, 0, and 3. Now my factors are going to be that negative 20x, and then the x squared minus 9, but that is squared, and then I'm going to have my answer. I'm going to pick numbers that are not those numbers. So let's say I pick negative 4, negative 1, 1, and 4. So when I put in negative 4, I put in negative times a negative, that'll make that a positive. If I put in negative 4, I'm going to end up squaring it, so it's always going to be positive, and I'm going to end up with a positive. If I put in negative 1, that's a positive. This is always positive, that'll be positive. When I put in 0, that'll be 0. Oh, I'm not testing 0, duh. I have my breakdown now. When I put in 1, that's going to be negative, and then this will be positive, and then the answer will be negative. When I put in 4, this will be negative, positive, negative. So I'm increasing from negative infinity to negative 3, union negative 3 to 0. Remember, you have to leave that negative 3 out because you're either increasing or decreasing. And that should make sense because if I look back up here, I have vertical axis up there. I'm decreasing from, where am I decreasing? I'm decreasing from 0 to 3, union 3 to positive infinity. So I'm writing my little soft note that here, this whole time here, I'm increasing here. Increasing. And here I'm decreasing. So I'm increasing here, decreasing here. Writing myself little notes, but I'm probably going to go back and check. So from here to here, not changing signs, so no relative extreme. From here to here, changing signs, so I'm increasing, hit 0, then I start decreasing. So 0 is going to be a relative max. Relative max at x is equal to 0. And if I substitute it back in, remember I already did that. I put 0 on for x and I got negative 1/9. So I'm going to have, so f of 0 is equal to negative 1/9. So I'm going to have a relative max at 0, negative 1/9. And again, I've already applied that point, that's going to be relative max. Then from here to here, I'm decreasing, so no relative extremes. So I only have a relative max. That relative max is already correct. Then it says concavity intervals, and it nicely gave me my second derivative. Oh my gosh, that's 60 times x squared plus 3 over x squared minus 9 raised to the third power. So to find my concavity, I'm going to find out what my second derivative is equal to 0. So I take the 60 times x squared plus 3, set that equal to 0. Divide by 60, I get x squared plus 3 is equal to 0. X squared is equal to negative 3. Go to take the square root, and I don't have any zeros. And then I'm going to ask myself, in the second derivative is undefined, and that happens again when this x squared minus 9 is equal to 0, and that x is equal to 3, or x is equal to negative 3. Making my table, I am going to have negative 3 and 3, so kind of similar to the other one, no 0. My things that I'm multiplying are 60, which is also positive, right? X squared plus 3. And then this x squared minus 9, which is now raised to the third power. And then I want my answer. I'm going to pick numbers, so let's pick that negative 4. Let's pick 1, and let's pick 4. So if I do that, so this 60 is always going to be positive. So I just put it there in case it was negative. If I do negative 4 and I square it, that becomes 16 plus 3, so this will end up being positive. Take negative 4, put it in there, that's squared, and it's 16. 16 minus 9 is a positive number, and a positive number raised to the third power is positive, so this will be positive. When I put in 1, that's going to be x squared again, which is 1, plus 3, that's going to be positive. When I put in 1, that's going to be 1 minus 9, which is negative 8. A negative number raised to the third power will be negative, so then this area will be negative. When I put in 4, it's going to be positive. Again, I'm going to have 16 minus 9, so that will be positive, and then positive. Again, if you don't like this, then you're taking this whole thing, putting in the calculator, and writing down what numbers you get when you put in negative 4, 1, 4, and just telling you the signs. So it's concaving up from negative infinity to negative 3, and then it also concaves from 3 to positive infinity. it's going to concave down from -3 to 3. So, and then my inflection points are going to be, since I changed signs here, I'm going to have to find f of -3, which should be undefined. And I'm going to have to find f of 3, which is also undefined, because those are my two restrictions on x, what x cannot equal, right, from here. So, since these two are both undefined, I'm going to say no inflection points going up here. So, I'm concaving up from -infinity to -3, and I'm increasing. So concaving up, so I'm probably going to concave up like this. Because again, don't want to cross that horizontal, can't cross that vertical. Concaving down, hit my max. I'm concaving down the whole time, but I'm only increasing from here to here. And then I start decreasing at this point, so from here to here. And then here I'm decreasing the whole time, and I'm concaving up the whole time, so I'm going to have a graph that looks like this. And that should be what my graph looks like. All right, I think I'm going to save the third example for when we're in class. I hope this helps, and I'll see you next time.